convert a decimal to binary. Okay, conversion from decimal to binary. Let's suppose I have a number. Let's suppose I have number as 56. Okay, this is a decimal number and I want to find out the equivalent number in binary number system. Okay, what is this equivalent number? So what do I do over here? I successively divide 56 by 2 and store remainders, okay, at each step. And then what I do, I just write the remainders from last to first. Okay, and then write the remainders from last to first. So let's take an example to understand what these steps are. Okay, we already have 56 in decimal to be converted to binary. Okay, so first I'm going to successively divide 56. Okay, so let's do like this. I divide it by 2. What do I get? I get 28 over here and I get 0 over here. Okay, here this guy, or rather this column, is the remainder column and this column is the quotient column. Okay, then let me just proceed further. Again I have 2. What is the quotient? 14. And what is the remainder? Remainder is 0. Okay, again divide by 2. Quotient is 7. Remainder is 0. Right? Again divide by 2. Remainder is 3. 3 into 2 is 6. Okay, and remainder is 1. Quotient 3. Remainder 1. Okay, let's proceed further. Divide it again by 2. Okay, my quotient is 1. My remainder is also 1. 2 into 1 is 2 and it leaves me a remainder of 1. Again I am going to divide it by 2. I see that my quotient is 0. 2 into 0 is 0 and I am left with 1, which is my last remainder. Okay, now this was the first step. Successively divide by 2 and store remainder at each step. Okay, let's not call this 56. Let's call it as successively divide the number. Okay, successively divide number. Okay, so my second step is write the remainders from last to right, last to first. Okay, so I'm now going to write it from last to first. 1 1 1 0 0 0. So my 56 in decimal is equal to 111000 in binary. Okay, so I have already given you the equivalent decimal value representation over here. Okay, so if if this is the equivalent binary value, then its equivalent decimal value should be 56. Okay, so let's verify this. Okay, so how do we verify? We verify it like this. Let me just write the indices over here. Okay, so I have my number as 111000. Okay, this is my binary number. I'm going to write the indices. Indices is 0, 1, 2, 3, 4, 5. Okay, so my equivalent decimal value is going to be something like this: 0 into 2 raised to 0. Just realize over here what I've said: equivalent decimal value for base k. Okay, in binary number system, what is the base? Base is 2. Therefore my weights is going to be in terms of powers of 2. Okay, plus 0 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3 plus 1 into 2 raised to 4 plus 1 into 2 raised to 5. Okay, so what is the final value? Final value is only 1 into 2 raised to 3 plus 1 into 2 raised to 4 plus 1 into 2 raised to 5. Okay, so this is 2 raised to 3 is 8, 2 raised to 4 is 16, and 2 raised to 5 is 32, right? And what is 32 plus 16? It is 48, and 48 plus 8 is 56. What did we begin with? We began with 56 and we ended up with 56. Therefore, this is the right binary representation. So this was my converting an integral part of decimal number into an equivalent integral part of binary number. Okay, now let's understand how do we convert a fractional part of decimal number. Fractional part of decimal number. Okay, the process is very similar, so I am going to copy these steps. Okay, I have it pasted over here, right? This was step number 2. My first step earlier said successively divide n by 2 and store remainder at each step. This is going to be modified as successively multiply. Okay, successively multiply n by 2 and store remainder part is going to be modified as and store fractions at each step. Okay, my second step was this is and store integers at each step. Okay, store the integral part at each step. Okay, and the second step is modified as write the remainders from last to first. Here we have write the integers not from last to first but from first to last. Okay, so let's see what we are doing. So let's take a number. Let's suppose I have this as a number in decimal and I need to have an equivalent binary fractional number. Okay, so how do I proceed? Successively multiply n by 2. Okay, so let's start. Let me have my number over here, 0.625. okay, multiply it successively by 2. Okay, what do I get over here? I get 0.625 into 2 is 1.250. My step says successively multiply by 2 and store integers at each step. What is the integral part over here? The integral part is 1. So I'll store 1 over here. Okay. So over here, this is my product and this is my integer part and this is my fractional part. Okay, integral part. Okay, now we are going to repeat this step successively until I get a 0 as fractional value. So I'll just add one thing over here. Repeat this until 0 is got as fraction. Okay, and over here, when do we stop? Successively divide n by 2 and store remainder at each step until 0 is got as quotient. Okay, just understand, we have 0 as quotient over here, that's why we stopped. Okay, so let's continue our successive multiplication. So after the first step, the fractional part is this 0.250. I'm going to multiply it by 2. What I'm going to get? I'm going to get 0.500. And now what is the integral part? Integral part is this, which is over here. Similarly, this, which is over here. Okay, that's it. Yeah, this over here. And what is 0.250? 0.250 is this. Okay, so next I'm going to write over here 0.500 multiply by 2. What do I get? 1.000. What is the integral part? Integral part now is 1. Okay, so this 0.5 goes to here, or rather make it like this here, and this 1 is over here. Right? Now that we have 000 as fraction, therefore we stop. Okay, the next step is to write the integers from first to last. So what I'm going to do, I'm going to write it as 1 0 1. Okay, so my 0.625 in decimal is equal to 0.101 in binary, right? Let's just verify that this is correct. 0.101, right? Let me just write the indices. This is 0, this is -1, -2 and -3. So What is the equivalent decimal value? Equivalent decimal value is 1 into 2 raised to minus 1 plus 0 into 2 raised to minus 2 plus 1 into 2 raised to minus 3, which is equivalent to 1 by 2 plus 0 plus 1 by 8. Okay, 1 by 2 is 0.5, 1 by 8 is 0.125, so my answer is 0.625, and this is what I started off with, so this is the correct answer. Okay, so that was about converting a fractional part of a number into the equivalent binary number. But just understand one thing over here, you might not always get 0, 0, 0 over here. Okay, for example, if my number was 0.624, let's suppose I had 0.624 and I wanted to get the equivalent binary number. Okay, so what I would do, I am going to write it like this. Okay, multiply it by 2, I am going to get 1.248. My fractional part is 0.248, my integral part is 1. Again, I am going to write the fractional part, multiply it by 2. What I get is 0.496, fractional part is 0.496, integral part is 0. I'll take my fractional part over here, multiply by 2, I am going to get 0.992. Okay, my fractional part is 992, my integral part is 0. Okay, multiply this by 2, I get 1.984. My fractional part is 984, my integral part is 1. I'm going to multiply it again by 2. What I'm going to get is 1.968. Fractional part is 0.968. Integral part is 1. Just realize over here. Let me just create a table out of it. Okay. So this is my table, and what I have over here is, this is the product, this is the fractional part, this is the integral part. Okay, so just realize I am not getting 0 in my fractional part of the product. I am doing it again and again and still I am not getting a 0. In that case, what I do is I just select the precision that I want. Okay, so I can say, let's suppose I say that I want this number with the precision of, say, 3 decimal places after decimal point or after radix point. Okay, so in that case what I am going to write is, I am going to say that my 0.624 is 0.624 is equal to 100. I am just going to take first 3 numbers in binary with a precision of 3 decimal places after radix point. If I wanted precision of 4 decimal places after radix point, I could write it as is equal to, I'll take the first 4 integers 1001. 0.1001. Okay, and similarly if I wanted 5 decimal place precision, I would write it as 0.1001. And what is the last? Yeah. So in this way I can go on proceeding like this until I get my required precision. But just understand, this is going to be an approximate value. We are never going to find out a correct value if we are not getting a fraction in which we have 0 in the product fraction. Okay? Until we get 0 in the fraction of the product, we cannot say that this is a correct equivalent value. Okay? These are all approximate values. This is precision of 3 after decimal places, precision of 4 after decimal places, and this is precision of 5 after decimal place. So how would we convert an number having both integral and, let's suppose, fractional part into a binary number? So let's suppose this is my number. What is the equivalent binary number? The process is, first, I'm going to write step 1, convert integer part. Second is convert fractional part and append. Okay. Step 2 is convert fractional part, and finally step 3 is append. So what is step 1? Convert integral part. So what is the integral part 56 in binary? It is, where did we do that? Yeah, it is 111,000. Okay, so first step 1, 111,000 in binary. Step 2, convert to fractional part. Let's suppose I want precision up to 5 decimal places. I'm going to write it as 0.10011. Okay, my step 2 is 0.10011. Okay, 0.10. Just understand, here I am not going to use the 0 over here. I am just going to write it as 0.1011. Okay, and the final step is append. So what I get is 111,000, and to this you append the fractional equivalent binary number, which is 0.1011. So this is the equivalent number that we are talking about. 56.64 in decimal is equal to 111,000.10011 in binary.